Good afternoon, everyone. Thanks for joining this Thin Film Society webinar. It's glad to meet you online today. Before we start the talk today, please allow me to quickly introduce the Thin Film 2024 conference. It is the 10th International Conference on Technological Advances of Thin Film and Surface Coatings. This conference is about, it is a biannual event of knowledge exchange and interactive platform for researchers and engineers from industry research labs and academics. This Thin Film 2024 will be held from 15 to 19 July 2024 in Singapore. So this conference, it covers a wide range of topics. It will bring together new developments on all aspects related to the processing, characterization, and the applications of thin film and surface coatings. If you are working on thin films and coatings, I'm sure you will find a symposium that matches very well with your research area. So we also publish papers, and this year, the selected papers will be published in Surface and Coating Technologies. It's a SCI Q1 journal, and we know that this journal is one of the top journals in the field of surface and coatings. All the submit papers still need to undergo the peer review process. Here are some important dates. If you consider attending this conference and want to give a presentation, you may need to note down some important dates. For example, like the abstract submission is due in the 15th of February. So it will due like in 2.5 months. So it's, I think it's a Chinese New Year time, so I would suggest you do it earlier. So finally, I would like to give a quick introduction about symposium number 7, which is the nanostructures, nanocomposite, and nanoparticles. This symposium will be chaired by Professor Sam Zhang and myself. So this symposium focuses on recent developments in both fundamental and applied science of nanostructured thin films and coatings. Particular attention will be given to the design, processing, characterization, and properties, performance, as well as applications of nanostructured thin film and coatings. When I say the nanostructured thin film and coatings, it includes a lot, like nanocrystalline, heterogeneous structured, graded or gradient, and also nanocomposite, multi-layered, as well as a porous film and coatings. And also, so if you are working on medium or high-entropy alloy coatings, including the ceramic coatings, you can also submit abstract to this symposium. And as you can see, we cover the processing and the characterization, the processing structure, property, performance relationships, as well as applications. So, yeah, if you're working on the thin film and coatings, you're more than welcome to join us in this conference. Look forward to meeting you there. Now let's start the talk today. My research mainly focuses on the development of mechanically robust coatings. Today I'm going to talk about how we enhance the mechanical properties of high-entropy alloy coatings through applying the metastability engineering approach. We know that surface degradation of engineering components that operate in harsh environments, such as high temperature, high stress, and highly corrosive environments, is one of the primary concerns of many industries. So therefore, protective coatings are widely used in a wide range of industries, such as aerospace, defense, energy, and mining industry. So it's to improve the surface life, performance, and the safety of many critical components. In doing so, it will reduce the downtime of this equipment and also reduce the associated cost. But often the problem with such coatings is that they are often made of ceramic-based materials. We know that ceramics, they are highly brittle. So they're very fragile under stress. So what's going to happen is a premature failure. This premature failure can affect safety and lead to negative economic consequences. As such, there is a pressing need to develop more durable protective coatings. That means the coatings need to be not only strong, but also tough. So they are highly resistant to fracture, not like the ceramic one. They often fracture catastrophically. So we know compared to ceramics, metals, they are ductile and highly resistant to fracture. We can see from the stress strain curves that metals, this blue one, this green one, sorry, metals show high toughness, but they are not as strong as ceramics. If we want to develop strong and tough metallic coatings, we will need to strengthen the metals to increase the strength. And at the same time, we can't lose too much ductility because we can see the toughness is just this green area below this stress strain curve. However, as we have learned from the material textbook that most conventional strengthening approach, they can strengthen the material, but at an expense of ductility. So that means the stronger materials are usually brittle. This is the strength ductility trade-off that has been lasting for many years in the metallic materials. And the ultimate goal of structural material, including the protective coatings we just talked about, is to make materials stronger without compromising ductility. That means for coatings, in addition to hardness, they also need to have the ability to undergo plastic deformation. So they can strong and tough. So our research aims to overcome this strength ductility trade-off, developing material with enhanced mechanical property through metastability engineering. The coatings that I have been working on are high-entropy alloy coatings. You may have heard of high-entropy alloys. They are a rapid emerging class of alloys that are quite different from conventional alloys. We know that conventional alloys is usually based on one principal element. However, the high-entropy alloy incorporates multiple principal elements, all in a high concentration. Imagine these elements as different fluids. The orange juice will be the conventional alloy, this one here. Well, this mixed juice will be the high-entropy alloy. We know that the mixed juice, they have more balanced nutrition and flavors. So that's the high-entropy alloy. With such a novel alloying strategy, high-entropy alloy offers a new avenue for realizing exceptional mechanical, physical, and chemical properties. High-entropy alloys show promise in overcoming the strength ductility trade-off that is common in metallic material. Therefore, they also offer a compelling prospect for long-lasting surface protection. But to overcome the strength ductility trade-off, we do need to apply some structural and mechanism design, such as metastability engineering. Now let's have a look at how the metastability engineering strategy works. Basically, it tunes phase stability. So as you can tell from its name, metastability, the word metastable means something that is not very stable. So in contrast to the conventional alloy design, we try to achieve the stable phase. In this one, we try to achieve the metastable phase. So we make the phase not very stable, so the phase transformation can occur. So the idea here, basically it tunes phase stability to promote formation of desired phase structure, such as the dual phase structure, and to trigger the formation mechanism. Normally, it's trip and twip. You may have heard of trip stew and twip stew. The trip is transformation-induced plasticity, and the twip is twinning-induced plasticity. So so the one here, we try to trigger the phase transformation and the deformation twinning. As a result, we will achieve high strength and ductility. Let's take an example. For if we're working on an HCP or FCC structure, we know that stacking for the energy is very important because all this deformation mechanism is closely related with this stacking for the energy. So if your material has a high stacking for the energy, the deformation mechanism, the deformation will be mediated by dislocation grading. If the stacking for the energy is very low, the phase transformation will occur. If you have something in between, the deformation twinning will carry out the plasticity. So when we tune the phase stability, it's important that we pay attention to this stacking for the energy. The metastability engineering approach is not something new. It has already been widely used in high manganese steel and titanium alloy to promote strain-induced phase transformation. High-entropy alloy are very suitable for applying metastability engineering. Since the high-entropy alloy concept, it widens the alloy design window for tailoring phase stability stacking for the energy and also the associated deformation mechanism. Therefore, the metastability engineering approach has been successfully applied into several high-entropy alloy systems. For example, this is the most famous one. This iron, manganese, cobalt, chromium metastable high-entropy alloy. So the idea here is to reduce the stability of the FCC phase through reducing the manganese content. The red color here is the FCC phase, and the blue color here is the HCP phase. As we can see, if we reduce the manganese content, we're reducing the stacking for the energy. Because the manganese is the FCC stabilizer, so less manganese means the FCC phase is not stable anymore, it's metastable. It starts to form the HCP phase. So that is the idea of the metastability engineering. In doing so, we can form this dual phase structure, both FCC and HCP. And another benefit of this structure is that during the deformation, because the FCC is metastable, and during the deformation, it will transform to HCP. We know that HCP is harder, so it will cause dynamic strain hardening. That will increase the ductility of the material. So as a result, we can see this is the metastable high-entropy alloy, and this is the single phase one. So we can see both strength and the ductility has been significantly increased due to the dual phase microstructure and also the transformation hardening. Normally, to apply the metastability engineering in high-entropy alloys, the phase stability is tuned by adjusting the concentration of metallic alloying elements. Like the example I showed in the previous slides. Another way to tune the phase stability is to add interstitial elements, but normally it's at very low concentration. We will talk about this later. However, in our work, we added a large amount of interstitial nitrogen to tailor the phase stability. The reason of doing that is, in addition to phase metastability, So the phase metastability will give us dual phase structure, deformation twinning, and phase transformation. And in addition to all this benefit, we will also benefit from the massive solid solution strengthening caused by high nitrogen intake. Let's talk more about this interstitial solid solution strengthening. So adding interstitial elements to high-entropy alloy was based on a few considerations. The first one, obviously, is about the solid solution strengthening. We know that the addition of interstitial elements enhance the solid solution strengthening, still causing this lattice distortion, right? Because it's changed the configuration of this lattice structure. And in addition to that, interstitial elements can also tune the phase stability. So it is possible to achieve excellent mechanical property through metastability engineering by controlling the interstitial content. So the phase stability also depends on the amount of interstitial elements that you have added. Another very important consideration is about the cost. Many of the current developed high and medium entropy alloys, they use very expensive alloying elements, right, such as nickel and chromium. We know that the application of high entropy alloy are greatly limited by their high cost. So to reduce the cost, we can adding these much less expensive interstitial elements, such as carbon, nitrogen, or oxygen. However, the challenge is that interstitial elements have a very low solubility in high entropy alloys, usually less than 2%, 2 atomic percent. What's going to happen if you add more than 2 atomic percent? The problem is you are going to have brittle ceramics. This brittle ceramic precipitate starts to form, which decreases the material's deformability, makes the material brittle. So it comes to a question, because we want to, if we can only add less than 2 atomic percent interstitial elements, it will not help us to reduce the cost. And also, if we want to enhance the solid solution strengthening and tune the phase stability, we may need to increase the amount of interstitial elements. Then it comes to a question that, is there a way that we can dissolve a high concentration of interstitial elements in high entropy alloy without the formation of brittle ceramics? The answer is yes. Magnetron sputtering can do it. If you're working on thin film and coatings, you should be quite familiar with the magnetron sputtering. It is a physical vapor deposition technique used for depositing high quality coatings. It's a bottom-up approach. So it's a very important, the rapid quenching effect, because it's a bottom-up approach. It deposits the coating layer by layer, atomic layer. So the cooling rate is super fast. The high cooling rate will suppress the diffusion. And if we suppress the diffusion, we will suppress the formation of nitride, because the nitride formation, the metal elements and the nitrogen, they need to come together to form the nitride, right? So if we suppress the diffusion, we are going to form the random or disordered solid solution phase. That means we can dissolve a large amount of interstitial elements. Right, this rapid quenching effect promotes the formation of disordered solid solution phase. So by using magnetron sputtering, we are able to produce a solid solution phase supersaturated with nitrogen without forming any nitride. So it's going to, this is what we would like to achieve. all these metal elements in the high entropy alloy, they just randomly distributed. And this pink nitrogen atom, they just sit at the interstitial sites, just randomly. They don't form nitride. Then we prepared 5 high entropy alloy coatings at different. We just use this magnetron sputtering technique, and we prepare the coatings at different nitrogen gas flow rate. We put it at 4, 8, 10, 15, and 20 SCCM. And we know that different nitrogen gas flow rate will give us different nitrogen content in the coating. So this is a schematic illustration of the magnetron sputtering. I'm not going to discuss too much on this. You just need to know the rapid quenching effect. It will suppress the formation of nitride and promote the formation of random solid solution. But normally, the higher the nitrogen flow rate, the higher the nitrogen concentration in the coating. So here I'm showing you the composition of these 5 coatings. As we can see, the nitrogen content, this blue line here, this green line here, the nitrogen content increases from about 7 atomic percent to about 30 atomic percent when the nitrogen gas flow rate increase from 4 to 20 SCCM. And at the same time, as the nitrogen content increase, all the metal content decreases. But the ratio between these 4 metal elements agrees very well with the target composition. So we have included such a high content of nitrogen in the coating, about 30%. Are we going to form a nitride? So we need to examine the microstructure. So here are the microstructure of the 5 coatings with increasing nitrogen content. They all show column nanograins. So from the low Mach TM, these ones here, we can see that the grain size increases with increasing the nitrogen content. As we mentioned in a previous slide, interstitial elements can affect the phase stability. Indeed, the high resolution STEM image here, they show the phase structure, and it shows that the nitrogen content has a strong effect on the phase stability and stacking for the energy of the high entropy alloy here. As we can see, it forms an FCC structure when the nitrogen content are relatively low. It's a single FCC phase. As we increase the nitrogen content, at a higher nitrogen content, they form a dual phase structure, both FCC and HCP, right? It's like a nano-layered FCC and HCP. The volume fraction of these 2 phases changes with the nitrogen content. So the highest nitrogen content is 28.9 atomic percent. But it's a high resolution STEM image. It doesn't show any nanoparticles of nitride. It looks like we have successfully dissolved a massive amount of nitrogen into the FCC and HCP lattice. But to confirm the solid solution nature, we have performed XRD EDS mapping. This EDS mapping at microscale, and also EUS mapping at nanoscale. All these results and these EDS and the EUS were performed at the N20 sample, the sample with the highest nitrogen content. If this one doesn't show any nitride, all the others should be solid solution phase. So we can see that all these results indicate homogeneous elemental distribution, and there is no nitride formation. Even if the nitrogen content for this one N20, we know the nitrogen content is as high as 29 atomic percent. So these alloys they're not yet nitride, but should be described as dissolved solid solution, supersaturated with nitrogen. So the conclusion from this slide is that no nitride formation. They are just a nitrogen supersaturated solid solution phase. Now let's look at the mechanical property. Basically just hardness and the Young's modulus. They all show, we can see all 5 coatings, they all show high hardness, but none of them show surface crack after the indentation. It's a spherical nano-indentation. And we didn't observe any surface crack for all the samples. But from the cross-sectional SEM image, we cut the indents using the FIB. We can see that the sample with the highest nitrogen, the N20, shows some lateral crack. It's not very clear here, but indicated by the arrows. While the others showed no crack, and at the same time, they showed large deformability. We also looked at the H/E ratio. This H/E ratio is an indicator of resistance against the elastic strain failure, which has a good approximation to rank the fracture toughness of hard coatings. As we can see from, it's a HB type plot, and this point is N15. It has the highest it has a very high hardness value, which is comparable to ceramics. As we can see, this hardness is around 20. We know the hardness of titanium nitride is around 20. So it's not yet nitride. This N15, it's still a metal coating, but its hardness is comparable to ceramics. And at the same time, it didn't show any cracks. It showed large plasticity. We know that titanium nitride is quite brittle, right? So that means this one is not only strong, but also tough. But what is the deformation mechanism that governs the plasticity? How can the coating sample deform plastically with such a high nitrogen content? To understand the deformation mechanism, we compare the microstructure before and after nano-indentation. And for the FCC structure, we selected 2 samples. One is N4 with the FCC structure, the other one is N15 with both FCC and HCP structure. So for the FCC structure sample N4 with a relatively low nitrogen content, we see that after deformation, extensive deformation twins were observed in the deformed sample, right? As can be seen in both low mag and atomic scale STEM image. So that means the deformation twinning happens during the deformation. And for another sample, N15, the dual phase one, the highly deformed region show a predominant HCP phase. So from a dual phase to a single phase, that means all the FCC phase has gone. So that indicates the FCC phase has transformed to HCP during deformation. Although we have added a high content of nitrogen, the high-entropy alloy still can deform plastically like pure metallic material. When its ability to undergo large plastic deformation combined with the massive solid solution strengthening caused by the high nitrogen intake, the material show excellent combination of hardness and toughness. So it's a quick summary of this study. Now we understand that nitrogen has strong effect on phase stability and the deformation mechanism. It's possible to apply the metastability engineering strategy in high entropy alloy coatings through adding high content of nitrogen. It can be nitrogen or it can also be carbon or oxygen. And the massive solid solution stem from the high nitrogen intake, provides high hardness. More importantly, even at high nitrogen content, they still have the ability to deform plastically like a pure metallic material. They can show deformation twinning and the phase transformation. So therefore, they shows high hardness and also high toughness. As we increase the nitrogen content, there may exist a sweet point at which we achieve the best synergy of hardness and toughness. And it may not be this one, the N15. We think it will be more efficient if we can use theoretical calculation to get the design of this metastable high-entropy alloy coating. So if anyone is working on the theoretical calculations or simulations, we are happy to collaborate. So next, I'd like to quickly show you another example of metastability engineering, in which the mechanical property are enhanced by dual phase transformation. In the previous study, the phase transformation is one step, and in this case, it's two-step phase transformation. Now let's have a look. This time we choose to work on chromium cobalt nickel medium entropy alloy. This is because according to theoretical calculation, the phase, the FCC phase observed in both chromium cobalt nickel alloy is the metastable phase, so which was retained by quenching from high temperature. We know that magnetron sputtering is the low temperature process, and the stacking for the energy of chromium cobalt nickel is pretty low or even negative according to the theoretical calculation. So it will allow us to form the dual phase structure, both FCC and HCP. And also the deposition rate here is also very important because the higher the deposition rate, the higher the possibility that you form planar defects like twin boundary and stacking faults. So here is the structural feature of this coating. We can see they have structural feature at a multiple length scale, right? Such a hierarchical structure allows for a unique combination of a variety of strengthening mechanisms at a multiple length scale. So the combination of this strengthening mechanism will give us the exceptional high strength and ductility. So as a result of the hierarchical microstructure and also the dual phase, the chromium cobalt nickel alloy coating that we have developed show excellent strength ductility synergy. So the mechanical performance was characterized by in situ micropillar compression test. As we can see, ultra high strength of 4.2 gigapascal was achieved. What does that mean? We can compare this one with the box sample. So we have the box single crystal sample, that is the same composition. We can see the strength has been increased by 6 times. So it's 6 times stronger. And with such a high strength, the nanostructured chromium cobalt nickel alloy coating, they still show appreciable ductility, as we can see from this stress strain curve. We found this alloy shows a very interesting deformation mechanism. That's the most important thing of this study. It's dual phase transformations. Basically, what we have done is after this micropillar compression, we prepare a TEM sample of the deformed pillar. And in that pillar, we see this shear band. And then we analyze the phase structure at different strength level. So if you're close to a shear band, the region has experienced the larger shear strain. So we check the phase structure in these four regions, then we found that the material has experienced the two-step phase transformations from FCC to HCP and then back to FCC. What is the benefit of dual phase transformation? We know that a single step phase transformation produces 35% plastic strain, but dual phase transformation will produce 70% plastic strain, which has been doubled. Right? That means the material's ability to absorb strain energy has been significantly increased. So that's a reason why this coating shows such a high strains and at the same time show large plasticity because it can deform plastically. And in a following study, we introduced the dual phase transformation to a BCC structure high-entropy alloy through interstitial co-doping. But this time the interstitial elements is at very low content. Our BCC structure high-entropy alloy shows an excellent combination of strength and ductility. We can see from this barrel shape of the compressed micropillar. And where does this ductility come from? It's just from this two-step phase transformation from BCC to HCP to FCC. So it's a mechanical property from this Ashby plot. We can see the mechanical property surpasses many other high-entropy alloys in the literature. Okay, to sum up, so this talk we mainly focus on the metastability engineering approach. So what we do is we promote the formation of metastable phase structures, such as the FCC and HCP dual phase structure. And we want to trigger the phase transformation and the deformation twinning, because this will give us larger plasticity that will make the material tougher. To achieve this, we use magnetron sputtering because the rapid quenching effect can suppress the diffusion and promote the metastable phase formation. With the metastability engineering, we need to form the metastable phase first, right? Another important thing, if you want to make the phase metastable, the composition is very important. So in the first study, we tune the phase stability by adding interstitial elements. In our study, it's a high content of nitrogen. And the magnetron sputtering allows us to dissolve a high content of nitrogen without the formation of nitride. That is the benefit of the magnetron sputtering. And also in the second study, the chromium cobalt nickel one, so we picked that composition because it's low staking for the energy. So we don't need to add any other interstitial elements because itself the energy is low enough. So if you want to design something metastable, you need to focus on the phase stability and the staking for the energy. That's all for today. If you have any question, I got my email in the first slides, so you're welcome to communicate through email. Okay, thank you, everyone. At the end, I would like to acknowledge all my collaborators. Yeah, that's it. Thank you.